beauty always involves relationship, right? I mean, beauty always involves a relationship in parts. You think of a beautiful Greek temple. It's all about the proportion of the different parts, the columns and the top, and uh, they are organized according to certain proportions. So beauty really is capturing this unity and this relationship between a diverse experience of reality and bringing it to unity. Okay, so if that's the definition of beauty, that's certainly found in mathematics and physics, because it does precisely that. It takes in a limited realm, right? In the realm of quantity, it does establish connections between different statements, different observations, and brings them together in a unified picture.
I'm Brandon Vaidyanathan, and this is Beauty at Work, a podcast about how beauty works in our world and shapes the work that we do. This episode is sponsored by Templeton Religion Trust and the Institute for Advanced Catholic Studies at the University of Southern California. More about them later in the show. Hello, everyone, and thanks for joining us. My guest today is Dr. Carlo Lancellotti. He is a professor of mathematics at the College of Staten Island and a faculty member in the physics program at the CUNY Graduate Center. In addition to his scholarly work in mathematical physics, Dr. Lancellotti has also translated into English and published 3 volumes of works by the late Italian philosopher Augusto Del Noce, and various versions of that have been published in a number of sources. And so, Carlo, it's such a pleasure to have you on the podcast. And you've written on this topic of beauty and science as well, and so it's really a delight to have you with us.
Thank you for having me.
Sure. Well, let's talk about what drew you to mathematics in the first place. What attracted you to this field?
Well, I came to mathematics from physics. I mean, my first degree was in physics, and I was always fascinated by the interplay between math and physical reality. It is truly amazing when one sees how nature, how the world is all intertwined with mathematical structures. I remember that my grandfather used to think that it's a proof of the existence of God. He once told me that. I mean, the fact that, that if you study physics, you find all these equations, all these formulas. I don't know if that argument is philosophically rigorous, because, one could say that the formulas are our own creation, and that they are not exactly what nature is. They're approximate. Of course, there are approximations, but there is certainly something there. And when you look, you look at quantum electrodynamics. You have all these abstruse calculations, and then you can reproduce the experimental result to 27 digits after the dot, or something enormous like that. It is very impressive. I don't think so. To me, the passion for mathematics was always about the intersection of mathematics and physics, but that's not true for many mathematicians. There are many what are called pure mathematicians, and they really appreciate, say, the beauty and harmony of very abstract constructions. Geometrical or algebraic constructions. Like since the time of Pythagoras, people have been fascinated by the pure form, the pure intellectual, the world of pure mathematical ideas. And every mathematician, or at least most of them, deep down are Platonists. They really believe
Yeah.
in the existence of a world of idea, and one of the main characteristics of this world of idea is harmony, beauty.
Well, that does seem to be, at least there's a perception. I don't know if anyone's actually empirically studied this, a perception that mathematicians care a lot about beauty. They talk a lot about beauty. Do you think that is the case, that beauty is an important concept, or?
I don't think anybody would do mathematics to get rich.
Right.
Okay, there is a subsection of math which is very applied, and you can somehow gain some kind of advantage in a technological sense. But most people who do math is because they like it. Now, sometimes there is let's say, not 100% good competitive aspect, right? Like mathematics would be like a nerd Olympics, like people competing to show that, or like, that they excel at solving problems, and so to show that you're smarter than the other guys who couldn't solve the problem. So there is that component, but certainly the aesthetic motivation is one of the top three at least, I mean, and people do like math again because they like to see how things are related in these structures that are very harmonious and very surprising. I mean, the great mathematicians are people who discover connection between fields that are apparently unrelated. Then you see that there is this thing that pops up where you don't expect it, and you can study algebra doing geometry, you can study geometry doing algebra, and a method that was devised to study some certain curves comes up in number theory. I mean, that's not my field. I do mathematical physics, but I know that people get very excited about these things, and certainly there is an aesthetic component to that.
What are the kinds of aesthetic criteria that mathematicians use? I mean, are there sort of a common set of things that mathematicians find beautiful in their work? I mean, you mentioned harmony, but what does it mean to a mathematician to find something beautiful?
Well, I mean, there are different things to art. First of all, there is universality, that you discover, for example, that a certain property that you discover in one example is amazingly general. And I don't know, like, the great theorems of probability, that you get the central limit theorem or laws of large numbers to an astounding generality, or I don't know. I mean, or people in number theory, they discover this very surprising relationship between sequences of numbers, and that you would, or you discover something that seems like very complicated, like could be, I don't know, the distribution of prime numbers obey some very simple statistical laws, right? I mean, I don't know. People have tried to prove the Riemann hypothesis, which is a conjecture in number theory linked to complex analysis using statistics or statistical mechanics. So there is the thrill of universality and the thrill of unexpected connection. I mean, I think that's what gets people going. And now, again, everybody has its own field. So I don't know. I studied a lot of statistical mechanics, which is a branch of physics which is very mathematical, and it's remarkable what you can say, for example, about how things happen in the limit in which you take the number of particles going to infinity, right? Because the in reality you never have infinite particles, you have 10 to 24 particles. But mathematically, you can take the limit as n goes to infinity of your equations, and that converges to a very simple limit. And this simple limit manifests itself in the physics, and that's very fascinating. It's very beautiful. I don't know how else to put it.
Yeah, yeah, yeah. Is there anything more you could say about your own experience of the work you've done? I mean, where is it that you've encountered in your own work what you would consider
Well,
beautiful?
I started, as I said, from physics. So I studied, I did my first thesis in the kinetic theory of gases, and I have a clear memory how amazed I was the first time I saw the Boltzmann equation. The Boltzmann equation is this famous nonlinear equation due to Ludwig Boltzmann, was a great Austrian physicist, and it describes the evolution of the distribution function for a set of particles in phase space. So you take a set of particles, each particle has a position and momentum, you send the limit of the number of particles to infinity, you want to study the density of particles in six-dimensional space. That's a complete mess, right? I mean, why would you expect that there was any way to do that? And then Boltzmann came up with this super elegant equation, which is, okay, it's a complicated equation, but the fact that it can be done, that the human mind can write down a law to describe something like that is, when I saw that equation, I was surprised. Wow, I would not never imagine that one could come up with something like that. It is an achievement. So that has been kind of my interest. And then, it is also, there is also a fascination in the fact that, that You can come up with equations, but then you cannot solve them. You know that there is always like the you can always you move 1 inch and there is you discover a new vistas of unsolved problems, and most of them are very hard. And so there is both the surprise of discovery and the realization of your ignorance, and there is something there, I don't know. When I was younger, I tried to study very simple solutions to describe a shock wave in a rarefied gas described by the Boltzmann equation. And that's the simplest possible problem, and it's so complex, that really, that there is, you see, you can study the solution numerically. You see, there is a very simple profile, but you cannot come up with a formula. And so there is, I don't know, there is the beauty that the model captures that, but at the same time, it escapes you. So it's a very interesting experience.
Huh, huh. Talk about the relationship between beauty and truth in mathematics, because a number of people have argued that beautiful equations are a guide to truth, or at least a reliable heuristic, and others think that this is a source of bias, and we
Yeah,
can't
like remember
really.
Dirac,
Yeah.
well, if there was no hope of finding a beautiful formula, people would not do this job, right? I mean, because at the end of the day, the whole operation of mathematical physics or theoretical physics is to replace uh, something very complicated with something very simple. I mean, that's another aspect of the beauty of it, right? That that you have a huge, complicated physical problem, and then you discover that there is one formula that, at least in principle, contains it. And if the one formula was 100 pages of formulas, nobody would care to discover it. You know what I mean? The simplification is part of the beauty of the process. In it's there is the reason to do it. If you couldn't find something like that, there would be no point. You would just, try to do a numerical simulation, particle by particle, but that would not be as interesting. And now the thing is that, so that's absolutely inevitable. The point is that, of course, our mind is not the mind of God, so to speak, and so sometimes there is the possibility of falling in love with a beautiful formula and expecting that that should be it, that because the formula is very mathematically elegant in its simplicity, in its richness of its structure, then that's the way the world should be. I mean, again, a famous example in my field is the Maxwell particles, that when in the 19th century, uh, after Boltzmann wrote his famous equation, the great British, maybe it was Scottish, anyway, British physicist Maxwell discovered that the equations simplify enormously and you find some super elegant solutions if the particles in question are attracted with a force that decays with the fifth power of the radius. So these are called the Maxwellian markers. So every kinetic theorist thinks that if I was God, particles in the world would attract and repel each other with a force that decays with the fifth power of the radius, which is not the way it is, because typically particles like electrons or ions, they use the second power. The Coulomb force between charged particles is 1/r², not 1/5, and that's a pity, because kinetic theory would work much better. And there is, generally speaking, this situation in which, for some strange reason, a lot of physical problems sit at the most hard to capture choice of parameters. Like a famous example is, again, the 1/r² interaction, which is typical of gravity and electrostatic interaction. And I know at least three different theorems that everything works for r, say, less than 2 or bigger than 2. But when you get to r equal 2, everything, all your math starts falling apart, right? And so there is a way in which reality sometimes does not correspond at the simplest, what we would correspond beautiful because we understand it, but sits at the boundary of it, and this drives mathematicians crazy sometimes. I mean, so I mean, the typical example of this beauty is the way people have been trying to, like again, theoretical physics, all this, you know, the standard model and stuff. People use that as a criterion, and this, and sometimes it works. I mean, I'm always impressed that, the way the number three, for example, pops up in very strange ways in physics. Like there is three dimensions, and that's very, if you wish, Trinitarian, because there is one space in three dimensions, and it is inseparably one and three. It is clearly one space, but it's
Right.
clearly triune, right? It clearly goes in three directions. Or you can find, or I like the example of the quarks. The quarks are organized in three triplets, so it's three square. But nothing. So there are all these beautiful numbers, and of course the people who invented the like Gell-Mann people discovered quarks wouldn't care about the number three in particular, but they certainly were much more attracted to a theory with three triplets than if it had been, I don't know, six times seven or something like that. You know what I mean? There is a certain elegance, a certain beauty to, for example, simple numerical groups or whatever.
Yeah, yeah, yeah. I mean, is that so how do people proceed? I suppose in theoretical physics, one of the challenges is this sort of drive towards simplicity, towards unification, even trying to develop a unified theory, right, of physics is something again that's very contested. Is that worth investing in? Is there reason to believe that reality at its core must be so simple as to be contained in a single equation or something like that, or is that a waste of time? How do you think of that?
Well, I remember you were telling me about, Wigner's sentence about the miraculous effect of mathematics.
Yeah, the
Reality,
unreasonable effectiveness.
reality
Yeah.
hints. I mean, there is again this experience that reality hints to very simple, elegant general principles, which at the same time always escape us, but so whether it's worth it. I mean, I think it is worth it, like it was worth, building great cathedrals. If it is in a strict, practical, technological sense, some of these things at some point are not worth it. But it is one of the few areas in which our time does something gratuitously, in which we do something just for the sake of the beauty of it. So, I mean, I don't begrudge the people who want to do that. I mean, the idea that science is to be useful, of course, within reason, is not correct. I mean, it is a spiritual activity in some sense. It is like also like poetry or art. So I think it should be pursued within reason. Um, Whether reality ultimately we are going to find the formula for everything, I don't think so. I mean, there is simply the problem of scale. There was an interesting book by, I don't know if you know David Bohm, probably, right? David Bohm, the American physicist. His case was that physics will always be incomplete because there is always the next scale. You can always look at something bigger, something smaller, something on shorter time, something on a longer time, and all your models at some point break, right? So if you go down closer and closer to the Big Bang, closer and closer to the microscopic Planck scale, at some point you need to change the model because it will stop working, and so there is in that sense a certain infinity uh, to physics. But what is remarkable is that within certain scales, you can describe the world with really elegant, simple mathematical models, and that's an amazing thing.
Yeah, how do you make sense of that? Because it's, I mean, from say like a strictly, evolutionary standpoint, there's no sort of reason to expect a priori that reality at any level could be described with what human beings, this sort of insignificant creature on a planet that's on a insignificant galaxy somewhere in space can actually grasp the workings of what seem to be laws that cover the expanse of the universe, right? Um, what is it about? Yeah, how do you, as a mathematician, I guess, make sense, or how do other mathematicians make sense of this unreasonable effectiveness of mathematics?
Yeah, I mean, I don't even know whether it's really that unreasonable, in the sense that, the world presents itself to us with a remarkable consistency, right? I mean, I don't know, it's not like a dream, recently I had a dream in which, in a dream, things keep changing randomly. One second you're clothed, the next second you're naked, the next second you're back in Europe, then next second
Right.
it is like the world is like a random association of images. Well, I mean, even without mathematics, the world does present itself to us as very stable in some sense, no, nosologically stable. I mean that it doesn't act up randomly, I mean, there is obvious regularities, and when there is regularities, there is math, I mean, it is not surprising in that sense. I mean, what could be a world like a random sequence of dreams? I mean, I don't know. It's a difficult question, I guess. But what is striking is more the, how can I put it? How again it can be boiled down to certain very simple general features, right? I mean, it's like, you can, because you could have a regularity that again fits in that in order to describe the world, you need to have a huge number of equations, for example, not just a few. I mean, that seems to me, again, you could describe, I don't know, like I always, another very striking, for example, set of equations is, general relativity, the Einstein's equation of general relativity. You can write them with one, two, I mean, I cannot count for you, but 6 or 7 letters, and all of the physics of very complicated systems are in those 6 or 7 Greek letters or whatever they are, if you interpreted them correctly. So it's a unreasonably, if you wish, simple model. I think that the simplicity is more striking than the existence of a model when it is simple. But then again, also the simplicity is deceiving, because then when you try to solve the equations, they are unbelievably difficult, right? So what is striking is that there is a simplicity of concept that contains an extreme complexity of behavior. I guess that's what's interesting to me.
What are the limits then to what mathematics can tell us about reality?
Well, it's abstract, I mean, this is true of physics in general. I mean, it abstracts one aspect of life, I mean, I always give the example of a beautiful statue. You go to the Louvre and there is the Venus of Milo, and she's sexy, she tells you about Greek history. How did she get, there is history, there is the human aspect. You can also you can measure the electrical conductivity of the Venus of Milo, but or you can, you are abstract. I mean, physics does not ultimately know reality. Knows reality. The scholastics would use the word qua, Q-U-A, right? For Thomas Aquinas and company, qua means with respect to, in the sense of, right? So physics only knows reality in as much as it can be measured in certain ways. It can measure length, weight, conductivity, luminosity. You can measure things, but of course, our experience of reality is much more than the experience of reality as measurable, right? We experience reality as beautiful, we experience reality as useful, we experience reality in terms of personality, we experience reality, even physical reality, we just don't experience it as measurable the way physics knows it, right? I mean, physics cannot tell you again if a body that falls down a window is a true gem that's worth $1 million or a stone or the same. You know what I mean? It can tell you the chemistry, but not the value, for example. You know, questions of value, the all economic dimensions is not. Anyway, I'm talking too much about a very simple point that physics abstracts one aspect of reality, but in order to do that abstraction, to extract this aspect of measurability and reproducibility, you have first to take in the world as a whole, right? And so the mistake is kind of to reduce that experience to the ensuing process of quantitative abstraction. Does it make sense?
Mm-hmm. Yeah. So I mean, so those abstractions are helpful to provide certain kinds of descriptions, but they don't really uh, exhaust other kinds of
Yeah,
categories,
exactly.
particularly as you're saying
Provide the
value
kind of
and
descriptions according to some aspect of the experience, right? I mean,
right, right, right.
you can tell me how if I jump off the window, physics can tell me how long it will take me to hit the ground, but that's not a lot about me. You know what I mean? It's not.
Right, right. So I mean, we typically associate beauty with art, right? With the sort of visual art or music or architecture or fashion and so on. But if we took, say, mathematics or even physics as a starting point for understanding beauty, what could that give us? Is that could we learn something about beauty that we typically don't think about?
Well, again, I think that there is the, you know, an aspect of beauty is its universality. Again, I mean, the fact that there is something that in the particular you find something which is universal. I mean, and so and the other aspect is that again the aspect of finding unsuspected relationships. You know, the way things are connected. I remember it was I think the great Italian philosopher Rosminio said that the definition of beauty is unity in diversity, right? And that's an interesting concept because beauty is not never uniform, right? Beauty can never be just a blank slate, or it cannot just be a complete jumble of differences. It is a beauty always involves relationship, right? I mean, beauty always involves a relationship in parts. You know, you think of a beautiful Greek temple. It's all about the proportion of the different parts, the columns and the top, and uh, they are organized according to certain proportions. So beauty really is capturing this unity and this relationship between a diverse experience of reality and bringing it to unity. Okay, so if that's the definition of beauty, that's certainly found in mathematics and physics because it does precisely that. It takes in a limited realm, right? In the realm of quantity, it does establish connections between different statements, different observations, and brings them together in a unified picture. So I think that's what it is.
Yeah, yeah, no, that's really helpful. I mean, one of the things that when we've been studying scientists for a few years, and when they talk about beauty, whether biologists or physicists, the common experience of beauty that where they really find profound beauty in their work is um, uh, in understanding. So this is the ability to grasp the hidden order or the inner logic of systems, and to say, ah, that's how things are. So there's a coming together of things, but also um, a sort of an experience of something being revealed to you, reality somehow revealing itself or disclosing itself, and grasping a sense of how things come together in that revelation. Um, and that seems to be, that phrasing of "this is how things are" has been, I found it echoed by poets I've interviewed, for instance, as well as scientists, and so there seems to be something in common across fields. Um, I wanted to ask about whether there's any sort of spiritual dimension to mathematics. I mean, I think for one reason, I think of people like Frank Wilczek, the Nobel Prize winner, who said that nature embodies beautiful ideas, and those ideas are expressed in mathematics. So as though in Galileo, I think said mathematics is the language with which God is writing the universe. But I also think about Islamic art over the centuries, particularly in their golden era, when so much of Islamic art was essentially like complex mathematics, it seems, embodying itself into various patterns. And I wonder whether you see any connection between um, yeah, mathematics and sort of the religious or spiritual sense in human beings.
Well, I mean, as I said before, mathematicians tend to be very Platonic. I mean, they tend to believe that there is a world of ideas. And, and I always say that one of the trends in modern physics has been towards increasing mathematization of physics, meaning that, in the physics of the 18th century, in a sense, bodies were extraneous to each other. I mean, it was the physics of artillery. You shoot cannonballs, you study the trajectories, and you use the math to do that. But at the end of the day, the body, the solid, rigid body, like the cannonball, is like kind of a given. Matter is a primitive concept. Now, the trend of physics has been towards kind of breaking down matter into, again, mathematical structures. If you look now at modern physics, it's not clear that there is matter. There is all these, representations of the Poincaré group, they're called, or whatever they are. When you study an electron, at the end of the day, or doing the standard model, you have this very sophisticated mathematical structures, and then somehow this sophisticated mathematical structure manifests itself as a tennis ball.
Right.
But reality has been kind of disembodied by modern physics, what I mean, because it's become so clearly identified with these sophisticated mathematical things. I think that's the reason why mathematicians and physics, I read some statistics, but you are the expert, tend to be more religious than biologists. Is that right? I mean,
It seems to be to some degree, yeah.
and I think that if it is the case, that's because they ultimately all their work is about assuming that the mathematical organization is primitive, is at the root of reality. While to some degree, biology is more like 18th century science. It's like a machine. You're like a mechanician who dismantles a watch, a clock, and see all the different parts move together, and then you bring them back together, but it's not as mathematized as physics, for example, right? Or even chemistry. So I think in that sense, mathematicians and physics would have a very hard time to say that that the mathematical realities don't exist, because it looks like, in fact, mathematical realities exist and then give us the impression of matter. But matter has become kind of a meaningless concept. You know what I mean? What does the word matter add to the standard model? I mean, you could argue that once you have all this group theory and Lagrangians and all these things, then there is the world. But why is it material?
Mm.
So this is also a problem with, at the end of the day, I think in the modern world, materialism just means predictability, because it means determinism, maybe, perhaps, even that after quantum mechanics is kind of problematic. But again, to a physicist, matter has been kind of boiled down to math. And then can you really say that math does not exist? Well, we live immersed in it in some sense, at least from a perspective of a theoretical physicist.
Right. Well, there are a lot of people who would say that they're not math persons, right? And they would sort of say that they don't quite get math, or it's not for them, etc. And are there ways in which beauty could draw people to mathematics or to science in ways that currently we don't quite see in our education system
Yeah, no, that's what we hope. I'm a math professor, and
yeah.
we always try to share our enthusiasm for applications. How math can shows up here, shows up there. Don't you see? Isn't it crazy how math comes up everywhere? It's beautiful. And some people see that, but other people don't. I mean, everybody's different, and so I work every day with some standardist the students who just doesn't care about math at all. I mean, and there is a bit of a push in our culture to try to explain that sociologically because nobody ever showed you, never had good teachers. You're a woman, they don't take you seriously. I mean, some of that could be true, but um, it's also true that math is not to everybody's taste because some people enjoy abstraction, enjoy patterns more than others do. Some people are more pattern oriented. At the end of the day, mathematics has a lot to do with the recognition of these universal structures that are kind of abstract. And again, some people are more have a greater affinity for that. I mean, did I answer the question? I mean,
Well, yeah, sort of. And do you have any tips, anything that's worked in your experience with your students, perhaps, in terms of better appreciating the beauty of mathematics?
yeah, I mean, I think that certainly would be good that mathematics be presented in close connection, for example, to physics already in high school. That would be a good thing. And also, I think the most important thing is that mathematics should be presented conceptually, because the big weak spot, at least living in the US, that I see in K through 12 math education is that there is a very mechanical presentation of math. Like math is about manipulating symbols and solving equations by doing step A, step B, step C. Uh, while mathematics is primarily about concepts, I mean, the ideas, and they should be presented as such, and the question of numbers, I mean, that's easier said than done, because then there is the opposite extreme, which has been in math education, which math education suffers from fads to an unbelievable extent. And some of the fads have been to, totally fuzzy it up, and focus on concept uh, without developing skills. You have to find a balance. People have been working on that because, of course, math is a big strategic interest with respect to the economy, technology. Everybody thinks that we have to teach math, but the teaching of math is still in some ways problematic. And I think that part of it is precisely there is this kind of utilitarian approach that math is for technology, and so you have to teach people certain skills. And you have to teach people to understand why people came up with math. So you need to have a conceptual, more, let's say, even philosophical approach to teaching. But this seems to be very hard to do. And yeah, I don't know why. It's a good question. I mean,
Yeah, I mean, I wonder whether, I mean, think of even better appreciating art or even becoming a more competent artist. It seems, I mean, we're living in an age that's much more specialized than, you think of periods like the Renaissance, where all the great artists were also scientists, and there wasn't this sort of clear separation. And it seems that,
so
knowledge
you
of mathematics would be helpful if you wanted to be a musician or an artist.
so you're advocating a connection between the teaching of mathematics and the teaching of art, or the teaching of
Yeah, I
mathematics and the
wonder.
teaching of science, or both?
Well, I think with the science now, I don't know if that separation is there. I mean, maybe with biology, people say there are people I know who move into one field or the other because they don't like the memorization of biology and they like the sort of equation solving, and so they move into something like mathematics or physics. But in terms of art, the separation seems very clear for a lot of people that I'm not a math person. I'd rather go and be a musician. And then, well, I mean, to become for instance, a good composer, you need to understand some of the mathematics. Um, so I just wonder whether you see ways in which, yeah, it's not simply about technology, but we could also sort of mathematics can improve our appreciation for art and even other kinds of fields.
Right. Yeah, I think it should be possible. If you look at proportion, for example, I mean, if you look at great art or perspective. All the projective geometry is everywhere in art. But more than anything, what is hard, I think, is to help people see the beauty of math as math, and why is because it is abstract, and so it takes a certain mind to do that. I mean, and to tell you the truth, I don't think that everybody needs to be, a great mathematician, of course. I mean,
Sure.
but it's important when somebody is taught something they understand. If they understand something very simple, it's better than doing more without understanding. I mean, and so I think there is a real race sometimes, to push people as far as they can without maybe just doing less better. I mean, I think that would probably be helpful, because then when people understand something, then they become more self-confident and they can move on and do more. But it is easy just to push people along class after class, and it builds on itself, and it's very unforgiving. And at some point you stop understanding, and then you proceed by inertia and all these formal manipulations, but it doesn't go very far. So I mean, it is a general problem in education, I think, that education being kind of utilitarian and technical, you measure the results without really appreciating where people are. That's, for example, one thing that strikes me, that for instance, in the US, all mathematics testing is written. When in my time, I'm from Italy, back I think the same was true of most of Europe. In order to get a math education, you have to take, since a very early age, you have to explain what you're doing orally, right? You have an oral examination. The way you are tested affects the way you understand. If you have to explain why you're doing something, what's the definition behind it, what's the theorem that you are going to use, immediately you are forced to think in a way different than if you have to sit down and just solve equations. So I think that ideally one should have also that kind of conceptual oral testing, for example. But at this point, it's impossible. And when people get to college, it's too late. It's a nightmare. They totally. I mean, it's not impossible. It's hard. And yeah, sorry, I went off on a tangent.
No, that's yeah. I think yeah, being able to sort of explain and have a narrative around it seems certainly an alternative to how we're doing things now. Well, Carlo, thank you for your time. This has been really fascinating. Great to learn more about how mathematicians think about beauty and what we can do, particularly to think better about beauty in math and science. Are there any references you might direct our viewers and listeners to get a better sense of some of the things we've been talking about today?
Well, the book by David Bohm, as I mentioned before, is interesting. He was one of the most philosophically oriented. When I was younger, I understood a lot about science and also math to a lesser extent by reading like Maritain. Maritain has some good books on the philosophy of nature, philosophy of science. My three ideas on the subject, I once wrote one article. I think it's in the Church Life Journal. If you Google my name, I wrote an article on beauty and science, more or less, and that's most of what I have to say, I'm afraid. But it's right there if you
Yeah,
want to take a look.
we'll put the links in our show notes. Thanks again, Carlo.
Yeah, you're very welcome. Thanks for having me.
Hey everyone, thanks for watching. If you liked that video, please hit that thumbs up button and share it with your friends. Also, please take a second to hit the subscribe button because it really helps us out. Thanks.